Welcome to the first session of the ICALEPCS conference, which traditionally is the project status report. There will be another status report session on Friday. My name is Markus Janusz. I'm from the Paul Scherrer Institute in Switzerland. And with my colleague Eugenia Hatziangali from CERN, we will chair this session. Before I am starting the session, I wanted to remind the presenters and the audience of a few guidelines for this session. To the presenters, please stay within your allotted time. This is 12 minutes, and then we have 3 minutes for discussion. And we will inform you 2 minutes prior to the end of this time, so after 10 minutes. And to the audience, please keep your mics muted at all times. And if you want to ask questions, please raise your hand in the Zoom application or write your questions in the Woowa question and answer tab. Don't use the chat, please. Otherwise, we have to check too many different places. And when you get the floor from us, then enable your video and the microphone. So now let's introduce the first speaker, which is Vincent Ardian from the MOAL laboratory in Lund in Sweden. Vincent is managing the software group at the MAX4 lab since 2012. Before he was at Synchrotron Soleil. And he has an extensive experience in control systems at synchrotrons and also a graduation in software quality. He is also a very active participant in the Tango community. He is going to present now, or the title of his talk is Maturity of the MAX4 Laboratory in Operation and Phase 2 Development. Please, Vincent.
Thank you for the introduction. So yeah, I will present the status of MAX4 and it will be a bit of the speed of light, and I will try to avoid any black hole in the meantime. So MAX4 is a Swedish synchrotron located in the south of Sweden, and we have also beautiful sunset light at this moment. This is autumn season. So this is composed with a linear accelerator and 2 storage rings. And we have 16 Beam9 funded already. And so MAX4 has been operated since 2017, and now we have 14 Beam9 that run at the same time. So in the last 2 years, there was a lot of focus on improving the stability and the performance from the user point of view. And one highlight on the accelerator where the control system has been involved is the orbit feedback that combine fast and slow orbit feedback thanks to the Tango control system. And this is running at 10 Hertz. So this is part of a bigger project portfolio that really try to aim to reduce all the small interruption. So, and nowadays we have improved a lot of this, and the downtime is more allocated with the system that need a lot of recovery. If you need more details, you can follow the talk of Johan Pettersson on Thursday on machine learning. So in the meantime, we have been pretty busy to have online 14 Beam9, and with a pace of in average 2 Beam9s per year. So the last Beam9s was Softimax and Danmarks. So they got the light in late spring, and already in September they got their first user. It's pretty fast. Meanwhile, we have also improved the Beam9 in operation, and for example, one Beam9 that can get their EXAF scan in 30 seconds and to have online processing. But recently we have COSACs, it's a beamline that we have started in last year. The user are able to assess the quality of the data on the fly because we have azimuthal integration processing directly in the data acquisition system. So we are improving a lot. And this is thanks to a new project organization called Central Project Office that manage all the projects at Max4. So they are in charge of establishing a project workflow that involves the different stakeholders. And this is in order to get the right priority and allocated resource to make sure that the project will be delivered on time. For the control system, so it means that we spend a lot of time adapting this to this new project management because it was agile is used as a project methodology. So we had to adapt and let's say that we are a bit in the middle ground and we still have the disadvantage of having two different methodology, and it means that in terms of quality, we have seen a reduction of quality in the delivery of the control system, and in the meantime, we had also the pressure of the operation for improving the beamline and the accelerator. So we have seen 4 different categories of issue. The first one is the reliability and performance, because the projects were really focused on the delivery of the feature and put it a bit aside the qualitative feature. We have also a problem of robustness. And this is mainly because we integrate equipment that we don't fully understand and we don't have necessarily the time to understand. Then we had also a problem of usability in the system, and this is mainly because even for the staff, the commissioning of the system has been greatly reduced, and in particular for the software, it's quite important to get this commission time for the feedback to rearrange the user interface. Then we have also some problem of responsiveness, and this is mainly due to a lack of resource and turnover in our group. So we started a project called KITOS, Kids Operational Support, and this is inspired by the European XFEL Data Operation Center. And this is mainly to focus on closing the gap with the expectation on the operation. And so this will be a crew of people that will proactively monitor the system, get, of course, the support from the user, but also try to follow up on the improvement in order to avoid the same mistake again and again. So in the meantime, we really try to improve the infrastructure of the control system. First of all, we have improved the way we deliver the software. I won't go too much in detail. You can follow the talk of Benjamin Bertrand on the control system management and deployment at Max4 on Thursday. We have set up a lot of monitoring in order to see the failure of the software, but also the hardware in this. So that's one part of the improvement. I continue with an upgrade of our hardware standard. And I would say we choose this incredible Panda box developed by Diamond and Soleil that help a lot the integration of new continuous scanning. And so it's more performant and more, reliable. So we gain a lot. So you can get more details with the talk of Eric and Quist on Friday on continuous scan with position-based trigger. So a lot of effort has been made focus on the detector, which is the most complex piece of hardware we can find on the bin9. As I say, we suffer a lot of not understanding the equipment. So we put a lot of focus on this, and now we are able to help for the site acceptance test and in the meantime, we allocated half of the resource really to target the data acquisition system. And this we have been able to simplify the pipeline of the data and to introduce streaming data with the RMQ. I'm not going into in detail, but we have set up in place set up a Kubernetes cluster, which called the DAC cluster. It's a central resource where all the detectors are sending their data, and there we have the ability to share the resource, to monitor the performance, and to increase the scalability when we need. So we use also Kubernetes for the general services, but running on a different cluster called OKD, which is an open source version of the OpenShift from Red Hat. And we also have another cluster for Jupyter Hub. We put a lot of effort on the data management, and we had a specific project, and we have upgraded the data infrastructure. Now we have tape storage. We are able to retain the data for at least 10 years now. But not only this project were focused on the hardware, but also on the services. And in this case, I would like to highlight the project that we are doing in collaboration with PSI and ESS. It's called SciCat. And now we are collecting the metadata on half of the bin9. So it's a really good project for us. A lot of effort on the user interface. And in this case, this is to increase the user friendliness. The staff are able to create their own user interface. I'm not going too much in detail. There will be a talk on Friday by Michael Guon on Tata, the no-code web dashboard in production. Then we have also on the scientific software, this is quite important. We want to invest in real-time processing. And in this case, there will be a talk on Friday by Zenek Mate regarding the FPGA, the azimuthal integration running on FPGA. We try also to avoid any, to reduce the human interaction on the experiment. And you can learn more from Isaac Linde. He will talk on Friday about automated machine learning based sample centering for MX with MX-MBot. We work a lot on the remote operation. I won't go too much in details. For reference, there is a video you can learn of how we have done.
Vincent, there are only 2 minutes left.
Yeah, great. So this is perfect because so I wanted to say that what our plan in the future. So we have also a soft X-ray free electron laser in the pipe. So it's at this moment it's in the conceptual design, and already we have. So the idea is to reuse the linear accelerator in order to have to increase the capability and to have this free electron laser. We have already started to have a concept of, to launch a prototype of the ondulator called ICALEPCS, and this is in collaboration with the LIPS Innov program. To conclude, our future is pretty bright. We still have a lot of challenge to do, and of course we want really to focus on the operation to get a bit more quality of service there. And in the meantime, to try to improve our organization, because, it's not only the soft X-ray free electron laser that coming, but also new bin9s, new detectors, new challenges all the time. So just to conclude, I would like to thank the diversity, because I think Max4 has the chance to have different culture. The staff, different gender, different background, and that's make really a chance for Max4 to be what it is today. And this concludes my speech, and I would like to acknowledge the kids group, the Beamline, the accelerator staff, also the NUC and Alice Wallenberg for the data stamp project, and also the collaboration of XFEL, SKO, PSI, ESS, and the Tango community. Thank you.
Thanks very much, Vincent. Are there any questions? Maybe one, we have time for one.
Yes, there is one question being posed.
There's one in Wover, yeah.
One question in Wover, yes. It's coming from one day. The question is, not sure I fully understand the reasons for loss of quality, and how do you plan to resolve them? How much does that come from the switch to Agile? And how much is just simply emerging earlier than expected?
That's a good question, but unfortunately, I think we need a conference for that, or maybe a workshop. I think I would be very happy to open a subject in VOVA to discuss and exchange, because actually, this is our experience, but I'm pretty sure there are different experience, and I think there are a lot of details in this, so I'm not able to answer within the time. But I will open the.
That's a good idea of opening.
Yeah.
Okay. So thanks very much again, Vincent, for this nice overview of Max4 activities. Virginia?
Yes, so now we move to the next talk on the status of integrated computer controls and information system for the National Invention Facility. This talk will be presented by Mike Fedorov, who is the leader of the team responsible for the software control system at NIF facility. So Mike, please put the microphone on, camera, and share.
Do you hear me, Eugenia?
Yes, I hear you very well.
Okay, very good. Thank you for the introduction, and thank you all for the opportunity to provide an update on the status of the control system. So I'm trying to move to my next slide, and actually it's not moving. So
Share and unshare, please.
yeah, I think I had having same problem like previous speakers. So let me stop.
Probably have to share the desktop.
Well, I'm not sure there's such option. Oh boy. Let me try to share desktop. There's no option to share desktop. Oh boy. Okay. Well, that's unpleasant.
Okay, that seems to work.
Well, yeah, might be moving. Okay. Since our last report of the previous 2019 conference, we continued our planned expansion of the control system capabilities, as well as advancing our long-term sustainability efforts for the aging hardware and software systems. Like many other facilities, we had to scramble to address a new challenge of the COVID-19 pandemics. Finally, I will be very pleased to report about significant progress towards fusion ignition. Okay, first about this unexpected interruption. Last year in spring, as COVID-19 epidemic spread across the west coast of the United States, A shelter-in-place order was declared in our county. Normal short operations of NIF had to be suspended, and our control and IT teams, we helped to transition the facility to minimal safe operations. Control room staff was reduced from normal 12 to only 3 operators. And we started to look for guidance, medical guidance on mitigation of COVID-19 hazards. And then we began reconfiguration of the control room. Operators were spread. I hope you see. You see my mouse. Operators were spread between the consoles. Some were moved into adjacent rooms. Plexiglass screens were installed, and ventilation flows were adjusted. Once we make it safe to be in the control room, we proceeded into restart of the control system. And the total downtime was just only about a month. We restarted experiments in May, and we received thank you, welcome from our sponsoring organization, the National Nuclear Security Administration. Okay. We started slowly and deliberately with our short campaigns, but soon after, NIF returned to normal pace of operations, as well as periodic maintenance activities, including our software releases. Traditionally, before the pandemics, to conduct such releases, our software engineers were joining operators in person in the control room, as shown on the left picture. With COVID-19 distancing protocols, it was not possible anymore. So we had to develop a hybrid approach to our software releases when our engineers work remotely, and they work together with operators who are physically in the control room. Our team has explored and experimented with various cloud collaboration, teleconferencing tools. At the end, we have settled on Microsoft Teams, Cisco WebEx, and Office 365 to coordinate and conduct our software releases. Picture on the right shows our team delivering a software release now from the cyberspace. Since June of last year, 5 major releases and 12 patches were delivered remotely this way. Even though our team is now back on site, we still continue with this remote release method because we have discovered benefits in productivity, efficiency, and ergonomics of this hybrid approach. More on this will be presented Wednesday by Ramel Lucuata from our team. Once the COVID-19 risks were mitigated, we returned to our primary mission, which is to achieve fusion ignition in lab conditions. Quick reminder that NIF is a 192 laser beam facility, which focuses 1.9 megajoules of laser energy into a cylindrical hull room, about 1 centimeter tall. Inside of the hull room, there is a 2-millimeter capsule with frozen deuterium-tritium fuel. The goal of ignition is to produce more energy from fusion than energy of the laser. Until 2020, our results were quite modest, with energy outputs of in tens of kilojoules, which is only a few % of the total laser energy. Okay. To improve fusion yields, we needed to understand better the processes within this small target on the time scale of nanoseconds during the implosion process. NIF has a state-of-the-art set of target diagnostics. There are 87 software-controlled instruments, which include over 600 peripherals of 55 types, cameras, oscilloscope, motion control devices. These devices capture rich information such as images and waveforms, using detectors in various parts of the electromagnetic spectrum, as well as particle detectors. A great example of a NIF diagnostic is a recently installed optical Thomson scattering system. We have 2 presentations in this conference. First, Adrian Barnes will be speaking about overall control system design for this instrument. and then Abdul Awal on specialized image processing needed for automatic alignment of OTS. Once we got a good picture of what's happening inside of the target, then we probably want to make some adjustments. And next step is to check the driver, the force which compresses the target. In our case, the force is a laser light from 192 laser beams. We should be very precise and uniform. One of the open questions which we had is to directly measure the energy going into the target after the final optics and frequency conversions. So last year, we fielded a new instrument called the Target Center Colorimeter, shown on the left, which is a large electromechanical system which places 4 very precise colorimeters at the target chamber center. With data from these colorimeters, we have improved calibration of the energy we deliver into the target. Another new instrument is essentially a room-sized lab called Precision Diagnostic Systems. There is a person shown there for scale. Unfortunately, I cannot actually use my mouse. Maybe I can. So NIF has a capability to divert one of its full aperture 40 by 40 centimeter beams into the system, which has numerous diagnostic tables to precisely profile laser light in time, space, and spectrum. What we could measure, we could improve. And with these precise measurements at hand, we started to implement enhancements to assure more accurate, more reproducible delivery of the laser energy pulse. We have also added a new wavelengths for color to our lasers. Multiple colors allow us to better control interaction between the laser beams. These efforts are continuing this year and next year. High fidelity pulse shaping project will upgrade our 15 years old hardware into modern. We'll have to develop low-level software controls, new pulse shaping algorithm, with a goal to achieve 4 times better short-term stability of the laser pulses. Another project is a flexible color mapping, which allow us to assign colors to the quads in custom configurations. As I have mentioned, fusion yield is the primary metric for NIF progress towards ignition. We have been making steady progress over 10 years. This winter, we got really good results when we broke through the 100 kilojoule barrier. And the latest very recent experiment produced more than 1 megajoule of fusion energy, placing us very close to the ignition goal. You hear me okay, Eugenia?
2 minutes.
2 minutes, guys. This event is a truly remarkable achievement of the broad international community, and it was covered by major news organizations. Okay. So with new promising results, it's opened a whole new operational regime for NIF, more physics to explore and more applications. It also confirms the need to prepare our facility for productive operations during the next 20 years. By 2020, we have transitioned, completed transition from legacy technology, VxWorks and Solaris to Linux, and from 8095 programming language to Java. Next step is to modernize our video acquisition systems. First developed as Windows proprietary platform, we are now migrating to open source Linux. Vinod Gopalan from our team will be speaking more today. Another project is migration of the embedded controllers. And another interesting direction is development of standalone control systems for new experimental lasers. And Brock Davis will be speaking about new framework, which is best suited for this fast-paced project. To summarize, controls team have helped NIF to mitigate the unexpected challenge of the pandemics. We achieved new great results on our 10+ years path towards ignition. Increased neutron yields add urgency to already planned sustainability efforts and renovation of the control system. NIF entered a new experimental regime, which requires development of new high precision, time-resolved diagnostics. That's all what I got. Thank you very much.
Thank you very much, Mike, for the clear talk, even though you have some difficulties at start. We open now for questions. Marcus?
Are there any questions?
I have one, if there isn't any.
Yes, I don't see any right now.
Do we have time for one question from me?
Yeah, one quick.
Mike, you said that you maintain remote releases because you found some unexpected benefits. I find that strange because usually when we release, we want the team to be as close as possible to the users. Can you just quickly go through the benefits that you found?
Well, actually, like I said, there'll be a specialized talk on this by Ramel Lucata from our team. But just looking one of our first pictures, software engineers are not very efficient just leaning, across somebody else's shoulder. We are much more efficient when we are sitting our workstations equipped with all the tools which we have, right? So this is one benefit. And again, Ramel Lucata will be speaking even more Wednesday.
Okay, thank you very much again for your talk.
Thank you.
Okay, our last presenter in this session is Juan de Santander Vela, talking about the SKA Observatory. Juan obtained his degree at the University of Granada in electronics development, electronics engineering. And then in 2014, he joined the SKA Observatory. And now he is the head of software product management in the operations group. Juan is going to talk about what the title of his talk is, From SKA to SKAO, Early Progress in the SKAO construction. Please, Juan.
Thanks, Marcus, for the nice introduction. Can you all hear me?
Yes, hear and see your slides.
Okay, perfect. And do they change?
Yes.
Did you? Okay, good.
The daytime.
Yes. So thank you, everyone. In this talk, I'm going to give you an update from a talk that I gave 4 years ago in ICALEPCS 2017. There we were in the pre-construction phase of the project, and we have now started the construction phase of the project. So it's very nice to be able to summarize on some of that. So this is the SK project, and the SK telescopes are built for studying the hydrogen, the neutral hydrogen in the universe. And there are many use cases that come with having a very large array with a lot of sensitivity that can see very far in the early history of the universe. And this is being done through a global collaboration of 16 countries. And the data that we will be generating will require a global network of SK regional centers. This is outside of the scope of the project, but needs to be developed at the same time for it. And we have a 7 to 8 years construction schedule, and the cost not just of the facility, but also of the operation for the first 10 years is going to be in the order of 2,000 million euros, 2020 euros. We will have 2 sites, Western Australia, the SK Low, with 256 antennas times 512. That's the 100,000 number that you have there, spread across 75 kilometers. And in South Africa, we'll have the SK Mid with 197 15-meter dishes spread across 150 kilometers. But this is what we call SK Phase 1. And we also trying to design SK Phase 2, which will have around 2,500 dishes across all of Africa and 1 million antennas across all of Australia. But even just with phase 1, this is just the largest collecting area of any radio array in the world. And this is a comparison. I'm not going to go through it, but you can refer to the slides later, where you see how much larger we are than any of the existing radio facilities that currently exist. So these are the partner countries. I told you we had 16 of them. The ones in blue are already members of the organization or planning to apply. And we have our global headquarters in the UK and the sites, as I said, in South Africa and Australia. And this is a project that has taken a lot of time to develop. The first concept of the hydrogen array was in a meeting in October 1990. So we were talking, the timeline here shows 1991 as the first year. And we moved forward to several projects that started. Prep Sky is a project that tried to prepare all of the governance. Then we had the SK organization being funded. That was a non-for-profit company. Then we had the site decision that came up with these 2 sites for our telescopes in 2012. And we have this preliminary design phase that took up to 2017. And then we have in parallel the treaty that negotiations for the intergovernmental organization. And that finally ended up with a treaty entering into force early this year, our first council in February, and then we had transferred the SK organization personnel into the SKO in the 1st of May of 2021. So we kept working on the design reviews, but one important thing here, I'm not sure if you can see my mouse, is that we started some software bridging activities. So we've been developing the software for the telescopes, or at least prototyping the progress for it, since mid-2018. And this distributed nature of the project with so many countries has its difficulties, but it's also has made it very resilient. And also we have staff that have shown a very strong resiliency, and has made this schedule not sleep too much because of this. And we had the start of construction planned for the 1st of July this year. So we had to compile very huge documents for the council to decide. This is more or less essentially what it does. And we had the Director General recommend the SK Observatory Council to approve this commencement of the construction, given all of the strong management and detailed information for the construction that we had. And this was finally approved. And then we had our T0, the start of construction, indeed on July 1st of 2021. So it's almost 30 years to the date, to this moment. What is the role of software in the SK project? This is a notional view of what the data flows for the 2 telescopes is. And essentially we go from around 9 to 7 terabits per second from each of the telescope. That gets processed in what we call the central signal processor. Then we have more processing that brings it down to a lower level of detail. And this is where we need most of the software. These are essentially 2 supercomputers of 130 petaflops each. So we will need a lot of data handling and data reduction software running autonomously here. But we will also have some real-time calibration loops that need to run in there. That also requires a lot of software. Plus, the SK regional centers, even when they are not part of the scope of the project, they will also need to share some of the software that we're doing. Plus, of course, all of the control software for all of these items and all of the digital signal processing firmware, which we are also managing as software. So what we've done so far is, let me see if this updates, is that we started prototyping, as I said, in August 2018, how to work in software. We're now in the 12th program increment from that moment. So we've divided the software in data processing, observation management and controls / correlators. This is where the what we call the visibilities are created, and then a transversal train, which is the services train that includes computing platform, networking, and systems that allow for release management and all of that. And we're doing this with the Scaled Agile framework. This is what we call the big picture. And we have a lot of people trying to generate what we call the program backlog so that the people can work on what we call the cadence. This is the management structure that we have. We have what we call telescope delivery teams. The telescope delivery teams indicate what needs to be released in terms of hardware, not just software, but in terms of all of the hardware. And so they are the ones driving the priorities, and we achieve alignment through these program increments. And then when we have software, the software is deployed and integrated at the product level. And this is a slide that we like to call the agile cadence ones. And you can see here that everyone is working to the same cadence from the developing, having some synchronization meetings here. And now we even have the telescope delivery teams since 2 PIs, so 6 months ago, they are also doing PI planning so that we can have a lot of alignment between what needs to be done at the different levels of the project. This is our software roadmap. Essentially what it is here, you can see on the top some of our milestones. And the main ones here, we had what we call array assemblies, and we introduced this array assembly 0.5, which is trying to bring forward some of the hardware that we can deliver so that we can start testing things earlier. And then we moved to what we call array assemblies 1, 2, 3, and 4, which was what we had planned at the time that I gave my previous update. And we had a few knock-on effects on this roadmap because of the hardware access related activities, but most of the delay in this roadmap came from the need for having the intergovernmental organization in place, and that's something that we have already managed to do. Then we have these 3 lanes for software development, and as you can see, we have them more or less cut out for delivering in each of the array assemblies. And then we have some lines for supporting the teams that will be doing the integration. And then
2 minutes left.
Yeah. Okay.
2 minutes left.
So yeah, that's fine. Sorry. So what we've been doing is prototyping the system integration. And this is done with a mixture of technologies using Tango for the control, containers, Kubernetes, and Helm for the deployment, the GitLab continuous integration, continuous delivery pipeline for testing. And then this is mostly Python with a bit of C and C++ for some of the devices and software. This is the control hierarchy that I presented 4 years ago. And this is how it's been implemented in what we call a Scampi. And this is how it shows in terms of deployments. Blue items are pods, green items are containers. And this is how we're testing that all of our infrastructure actually works and as intended. We use Tango in a very event-oriented way. So we find in some edge cases around the event mechanism, and this requires some sustained effort directly on Tango. But we hired one developer for that, and he will be just contributing 50% to the Tango community directly. We also find in some containerization orchestration challenges, but the Tango collaboration is also as a whole doing that, and we joined it in 2017, so that's also helping. And then some of the other challenges that we're finding, one of the good things is that we're finding them now. We are only 3 months away from our start of construction, and we already know about some of the challenges that we will need to tackle instead of finding about them at the integration points. So just to finalize, the next steps is to keep aligning the construction proposal, what we call the integrated product schedule, which is hardware oriented, with the software roadmap, which is functionally oriented, to finish the contracting, to move from the bridging to construction funding. We're finding that the system and platform teams are not, it's not easy to find people for them. And we hope that setting up the contracting framework will help us there. We will also need to keep improving our Tango base and the iteration of the moving from the prototype integration to the software that we want to deliver. So I have a few slides that I will quickly go through, but these are things that are interesting for people who are interested in the SKA. So thank you and questions. And I just wanted to also thank the people from the Safe Solution team, the TDTs, our developers, and the Tango collaboration. And a shout out to my father-in-law who died recently.
Thanks very much, Juan, for this very interesting talk. In view of the advanced time, I think we have to stop here. If there are any questions, please address them directly to Juan. And I'd like to, with this, I'd like to close the session here. Thanks everyone for joining. Enjoy the ICALEPCS, and thanks again, the speakers. Have a good conference.
Thank you.
Bye.